Welcome to this lecture on digital computer electronics. We are discussing about the circuit algebra. The circuit algebra is the modified form of the Boolean algebra given by Claude Shannon in 1930s. It is studied under the title Boolean algebra. So we'll be covering the Boolean algebra and logic circuit minimization in this lecture. Boolean algebra and minimization. In the Boolean algebra, we'll come across the term called min term. Is actually the variables in logic AND. If A, B, C, D are four inputs to an AND gate, the output Y is written as Y equal to A and B and C and D, and or A, B, C, D. This is known as min term. The terms in the variables in AND are called min terms, or we say sometimes products. Another term called as max term. The variables in logic OR are known as max terms. If A, B, C, D again are the inputs and Y is the output, then Y is equal to OR of A, B, C and D. The max terms are also known as sum. Now we have the other term called as sum of the products or SOPs. Is actually the min terms in logical OR and are called sometimes sum of products. In other words, SOPs are different AND terms in OR to form expressions like Y equal to A, B, C, D or A, B, C or A, B. Another term Y equal to A naught B, C, D or A, B naught C, D or A, B, C naught D or A, B, C, D naught or A, B, C, D. Then another term which is again coming sometimes in the study is product of sums, called POS, product of sums. These are actually known as max terms in logical AND. So the max terms in logical AND or known as POS, product of sums, and represented like this, that y equal to OR of A, B, C, D and OR of A, B, C and OR of A, B. Another term, y equal to OR of A, B, C not D and OR of A, B not C, D not and OR of A, B, C not D. Now continuing with the representation of Boolean expressions, let us start with an expression in sum of products A naught B naught C D, or A naught B C naught D, or A B naught C D naught, or A B C naught D naught, is an expression of odd minterms. But in actual real digital electronics, you may say it is an OR of ANDs. In the similar way, product of sums, an expression of ANDed max terms, but what it is actually AND of ORs. Let's go for the implementation of these expressions. Let's take the first expression, sum of products, or I may say OR of ANDs. The expression needs 4 input, 4 AND gates and a 4 input OR gate. Also we need 4 NOT gates to produce the NOT of all the inputs, A naught, B naught, C naught and D naught. So the circuit in total requires 4 input AND gates, 1 4 input OR gate and 4 NOT gates. We saw that the expression requires 4 NOT gates, 4 input AND gates and 1 4 input OR gate. The hardware may be maximum, but we can minimum this hardware by just solving or simplifying the expression. So how we can do that? Let's see that we take BC bar or BC naught common from the second and the fourth term, and in the same way take B bar C common from first and third terms. Then the expression is like this, and if we now take A D naught or A naught D common from these two terms, we get two terms in AND. But what these two terms indicate is an exclusive OR operation. So the representation can be very simple. Now the Y function is simplified to A exclusive OR D and B exclusive OR C. Now if we have the circuit for this implementation, it is very simple circuit. No AND gates, one AND gate rather, one AND gate and two exclusive OR gates implement the same function. So this is called the minimization of Boolean expressions. What minimizes the Boolean expression is actually minimizing the hardware circuit required for the function. Now let's take the second Boolean expression, product of sums. The expression in the bottom requires one 3-input AND gate and 3 4-input OR gates along with 4 NOT gates. So again, this hardware can be more. We shall go for the minimization of this expression. So using Boolean laws, we can minimize this to this expression, and this expression can be implemented with this circuit. So we have again reduced the hardware by simplification of the Boolean expression. So continuing with the minimization of Boolean expressions, let's consider a function y equal to a b c d or a b c d naught or a b c naught d or a b c naught d naught. If we go for the implementation of this Boolean expression, the circuit for this expression requires 4 input AND gates and 1 4-input OR gate, and in addition we require 2 NOT gates. But if we try to minimize this expression, we finally reach that y is equal to AB. So if we implement now the y function, it will be a simple AND gate, one AND gate. We continue with the implementation of Boolean expressions. Let's take a problem. A company has 4 shareholders with 60%, 20%, 10% and 10% partnership. Design a logic circuit that will ring a bell when a bill is passed by them with their partnership vote of 70% or more. So how we will try to solve this with a digital circuit? Let's see the solution. Let the shareholders be A, B, C, D respectively in the 4 variables. The possible choices for passing of the bill with 70% vote are ABCD, ABC, ABD, ACD, AD, AC or AB. Will not directly implement this. This will require a bigger hardware. Let's solve this. And when we try to solve this, we finally arrive at the solution y equal to AB or AC or AD. If we take A common, we reach A and B or C or D. Now if we try to implement this circuit, it's a very simple circuit. So the 4 shareholders will have the key buttons A, B, C, D according to their vote, and whenever they press with 70% or more than 70% vote, a bit will be generated at Y which can ring a bell. So continuing with the simplification of Boolean expressions, let's have the set of 5 problems. We'll try to minimize them and implement them. So take it an assignment and try to first minimize these expressions at your own places, and then you can share also with me if you have some problems for the minimization and implementation of these expressions. Now let us stop here for this lecture. Best wishes. Thank you very much.